Okay, welcome back to statistics in real life. So now we start getting into some of the more specific topics. So we're going to start here with the idea of population and samples. So to reiterate, our eventual goal is to take a sample of data and use that to make conclusions about the population. To take a sample of voters and try to predict the outcome of an election. To take a sample of recipients of a particular drug and try to determine whether the drug is useful, how it's going to work in the population based on that sample. So it's fitting that this is the first topic we talk about because the difference between populations and samples is very important. I think this is a topic that most people have an instinctive knowledge of. In other words, we know generally what a sample is. So a population is what we're trying to study. So it's any specific collection of objects of interest or people of interest, for that matter. And a sample is what you're actually basing your conclusions on, because in no study are you ever going to have access to the population. Like I said, if you're doing a drug study to find out whether a drug is effective or not, pharmaceutical company, you obviously can't test every person who's going to take the drug. If it's a political poll, you can't poll everyone in the population. We don't have access to the entire population. So what we try to do is gather a sample and use that to make an inference on the population. And when I talk in the last lesson, in our intro, about descriptive versus inferential statistics, this is the process of making conclusions. So we're going to talk in the next module about descriptive statistics, and we're generally going to assume that we're dealing with samples. That's the way we may have some population examples in it too. But what I want to do here in this lesson, my goal is to just go over the differences. I mean, it's pretty intuitive, population versus sample, but there are some specifics that need to be discussed. And that will prepare us for collecting and sampling and displaying data later on. Okay, so there are a couple other vocabulary terms I want to talk about here. And I'm not really big on vocabulary normally, but when you see a word or hear a word used later, you should know what it means. So a parameter is a number that describes some aspect of the population. A statistic describes the sample data. So an easy way to remember this, parameter for population, both P's, and statistic for sample, both S's. So a statistic is a calculation not of the population, but just of a sample of it. If you take the average of an entire population, it's actually called a parameter, which, when you think about it, when you see, for example, in a football game, the halftime statistics, or let's say you have a quarterback that completed 60% of his passes in a game. Is that a statistic or a parameter? Well, it depends on how you view it. If you're talking about, it depends on how the population is defined. If your population simply consists of that game, then the 60% is a parameter, because that is the entire population. But more likely, you're using it as a measure of that player's performance over a season or over a career, in which case that 60% completion, and again, you can apply this to any other sport, a 250 batting average or field goal percentage in basketball. Most often when we talk about statistics, you're trying to take a performance from a game and project what that means for the player's career or for the team's season. So from that standpoint, it is statistics, but it does depend on your point of view to a certain point. Another example is if you're talking about the average in a class, an average test score in a class. You can look at that class as the population, in which case the average is a population parameter. But if you're trying to use those results, those calculations, those statistical results to infer about, all classes or all students or all freshmen, whatever, then you're treating it as a statistic. So that's the difference between the two. And the other term one of the other terms I want to go over here is sampling error. Now, I want to be very clear on something about the word error. In statistics, an error does not necessarily mean a mistake. When you see the term error, what it's basically referring to is the fact that you don't have access to the entire population. We'll see this in an example in just a few moments. But, and I'll kind of demonstrate what I mean by sampling error, but it just means that there's a difference between your sample data and the population data, and that difference occurs not because a mistake was made, but because you don't have access to the entire population. So there's a very high probability that your sample average, let's say, will not match the population average. Again, we call that an error, but it's not a mistake. It's just, it's what happens because you don't have access to all the data. I want to get into a sample problem from late in a statistics course, something that we'll be looking at eventually. A bottling machine fills 20-ounce bottles of soda. It is suspected that the bottles are being underfilled. A sample of 36 bottles are taken, and the mean, or the average, of the population is 19.2 ounces. So this is the sample statistic. What we're concerned about is, does this mean that the population is at or under 20 ounces? There's a reason I'm putting a question mark here, because we don't know what the population is. But we're trying to use this sample to make an inference about this population. So we're going to learn to solve problems like this later. And in actuality, we don't even have all the information we need. There's other things we would need to know about the situation to actually solve it. But we're saying 19.2 ounces. Well, it's certainly below 20 ounces, but is it far below enough to say it's not a coincidence? Because you're going to have sampling error. Not every bottle is going to be exactly 20 ounces. Some might be a few tenths of an ounce over or under. So the question we're asking is not, is 19.2 lower than 20? Obviously it is. The question we're asking is that evidence that the average of the population is under 20? That's what I'm going to make that distinct difference. And that's why I'm kind of introducing a problem like this now, even though it'll be a while before we're able to actually solve this. But that's what we're working toward. Okay, I want to go through just an example of what I mean by sampling and sampling error. So what we have in the table below, and this is only part of the table, it's a list of the average SAT score in every state of the United States. Again, I can't fit the entire table in here, but last 12 items here. So we can take all 50 states, if we had them in this list, we could take all 50 states and find an average. And we're going to talk about mean and median and mode. When we talk about the average, we're generally talking about the mean. We're generally talking about the mean. So the mean is going to be actually I should stay away from symbols right now, is the total of all the numbers divided by the number of data points. So in this case, you would add up all these numbers and divide by 50. So that's what we mean by average right now. So if we did that, we would find an average or mean, population mean, of 1073.4, about 1073 SAT average. Oh, and by the way, I realized this symbol here, That is the Greek letter mu, at least the lowercase version of it. And that's the symbol we generally use to describe a population mean. If the average we're talking about is of the entire population, if the average we're talking about is from a sample, then we have then we use a different symbol for the average or the mean, but it's going to be X bar, an X with a line over it. So we have two different symbols. Both of them are referring to the mean or the average. And we're going to get into this a little bit later on, calculation of mean, calculation of average. But since we're talking about population and samples, I need to at least introduce it now. So this means the calculations were taken from the sample, and this means they were taken from a population. They're going to be, the process for finding the calculation, for finding the number is the same. But the difference is the population mean is constant and the sample mean is going to change depending on the sample. So we have in this table here, we have a random sample of 10 states. So this, in this case, this is the entire table. We selected 10 states at random, and we had an average here. Let me highlight these numbers. Of 1079.6. Now, of course, it's not equal to 1073.4, and the reason it's different is because we're not adding up all 50 numbers. We're only adding up a sample of 10. So obviously that's going to result in two different numbers. We're dealing with different data sets. One is a population, one is a sample. And that difference is the sampling error. I talked about sampling error earlier. So the actual value is 10, I'm just going to round these off, is 1073, and the mean, actually it's the other way around, 1080 minus 1073, so the sampling error is going to be about 7, because the sample is 7 higher, roughly, approximating here, but the sampling, the sample mean is 7 numbers higher, 7 points higher than the population. So we've overestimated by 7. And again, this doesn't mean that there was a mistake made. Error just means, well, we don't have access to the entire population. So what do you want? You know, we're dealing with the data that we have. So it doesn't mean a mistake. It just means we don't have access to everything. And as I said, the two different symbols. And again, we'll talk more about that later, about the actual symbols and the calculations. But what you need to understand for now is just the difference between finding data from a population versus finding data from a sample. For a lot of statistics, for a lot of calculations, the formulas are basically identical. The process is the same, not for everything. There are some calculations where it does make it, the formula does change depending on whether it's a population or sample. But the formula is generally the same. You add up and divide by the number. So this is what I mean by sampling error. We could take 4 more samples. And so we have, 4 more, if we take, 4 samples of 10. So we take, every time you take a random sample, you're going to get a different group of 10 states. And the sampling error means that these are all going to be different. No, it was 1073. These are all going to be different from the population mean. What was the other one? 1079.6. So the sample means are going to differ because every time you shuffle, look at it as shuffling cards. Every time you shuffle the deck and you pick the top 10, you're going to pick different cards. You're going to pick different states. And that's really all that's going on here. That's the key point here. Now, here's where we're eventually going with this. Suppose we did not have access to all 50 states, the numbers from all 50 states. Now, in this case, it's easy enough to look it up. But what we're going at eventually is we're not going to have access to the entire population. So we are not going to know what this is. That's going to be ambiguous. We're not going to know what the population mean is. And we're going to have this sample data, and we have to make inference. That's what statistical inference is. The descriptive statistics are calculating these numbers. That's the descriptive part. The inferential part is saying, okay, we have this information, so what? What does this tell us about the population? That's the inferential part. So, again, I'm not going to read the entire paragraph here. You can see it on the screen. Basically, to kind of paraphrase, if we get, for example, the 1071.1, suppose that's the sample data we get. Well, we're going to say that the population mean is going to be 1071 plus or minus some margin of error. You see margin of error on polls all the time. 46% plus or minus 3.5%, that type of thing. So 1071, we're going to say the population mean is 1071 plus or minus some margin of error. Now, how we calculate the margin of error, that we're going to find out toward the end of the course. But the idea is that's what inferential statistics is, and that's what we're building toward. So I use 1071, but again, whatever sample data you get. So more generally, that's what we're dealing with. That's the basic equation we're dealing with, and we'll see some more detail on this as we go. And one goal of statistics, of course, is to describe and understand sources of variability. And this is one source right here, the fact that you have different samples, and those different samples are going to show you different numbers. I want to go through an example here, but we're talking about samples and how you gather a sample. We're not really going to go too much into this course on sampling. You could have an entire course just on sampling. It's a very deep topic, and the details are going to be beyond the scope of this course. But one thing you have to be very careful about is bias in your sample. You have to make sure that your sample is representative of the population. And I have an example here, is from the 1936 presidential election. So I tell this story in all my statistics courses, so I'm going to go into it briefly here. 1936, so we're in the early days of presidential polling. Presidential polling is a very new thing, or any type of political polling is a very new thing at the time. And there was a magazine at that time called the Literary Digest. And they had this novel idea of polling the population and using to try to predict the winner of the election. And in 1936, you had the incumbent Democrat, Franklin Delano Roosevelt, and he had a Republican challenger by the name of Alf Landon. And so what the Literary Digest did is they made postcards or ballots, right? And they mailed it out, and they mailed out about 1 million. And they got about 1 million of these things back, which is enormous. That's an enormous sample. You can get a pretty good idea even with as low as 1,000 voters if you select them properly. And this sample was not selected properly, because what happened is when the magazine, when they tabulated all the votes, they made a prediction that Alfred Landon, the Republican, would win in a landslide. Now, most of you have never heard of President Landon because there was no President Landon. In fact, the result was just the opposite. It was Roosevelt winning in a landslide. So what happened? Well, we're going to figure that the calculations were correct, and the million, I don't know if it was actually a million postcards, but if it was, that was plenty more than enough. You can get extremely accurate. You could get within plus or minus 3% with as little as 1,100 people. So a million is huge. So the problem is more of how they selected their sample. So they mailed out the cards to their subscriber list, obviously. And who else? Well, they looked at phone directories, automobile registrations, things that would be pretty common today. It's not a big deal in 2018. But in 1936, what's happening in 1936? The Great Depression. Cars and phones were luxury items. They tended only, the rich you had to be rich to have a car or a telephone. That's not the case now, but in 1936 it was. And I also might say that if you've lost your job, if you're in an economic depression, probably one of the first things to go is going to be magazine subscriptions. So chances are their readers were on the wealthy end as well. Now, again, it doesn't have to necessarily be the case that the rich are more likely to vote Republican. Anytime you see any factor that could potentially be a difference, that where that people with that factor are going to be more likely to vote a particular way than without that factor, you have to account for it. So if there's even a possibility, that's why you have to be political pollers. How do you select who to poll, who to ask? And there's an absolute science behind that. And like I said, we could go way into the weeds on this, but you have to make sure that your sample is an accurate cross-reference of the population. And whatever the voting tendencies of the wealthy were, the bottom line is the Literary Digest sample was not an accurate, it was not a representative of the population. You're getting people who may vote overwhelmingly in one particular direction. That's basically what happened. And so, polling organizations, since then it's become an absolute science. If it's done properly and unbiased, you can get very accurate results, and even from samples of only a few hundred, it is really enough. Okay, this is kind of went over this already, the descriptive versus inferential. Again, descriptive statistics is making the calculations, finding that sample data. Inferential statistics is the process of making conclusions about the population average. And again, the actual process of inference is something we're going to save for the last few lessons of the course. But right now, I'm trying to give you the overall picture. Okay, the last topic of this lesson is on the idea of random variables. So you're used to seeing variables. You've probably seen variables if you've taken an algebra class. You're solving equations for variables. 2x equals 6. So this is how we're used to seeing variables. And I promised very little algebra, but I'm only doing this for demonstration purposes. In fact, the variables that we're dealing with here, for the most part, are what we call random variables. So in the equation above, 2x equals 6, x has a fixed value. It has a value of 3. We don't know that it's 3 until we perform whatever equation solving processes that we use. But it has a fixed value. We just have to find it. Random variables, the idea of a random variable is it does not have a fixed value. It doesn't have a value until an experiment is performed. So, for example, you could roll a 6-sided die. So we'll take a random variable x, and generally we use capital letters for random variables. X equals the number of dots that comes face up on the die. Well, what is x? It's not something you can solve for. You roll the die, however many numbers come up. If 5 dots come up, then x equals 5. If 4 dots come up, then x equals 4. It's not the result of a calculation. It's the result of an experiment. Now, I know we're doing calculations. We did calculations to find out the mean, but those are the statistics. I'm talking about the actual data itself. We don't know what an individual data point is until we perform some experiment or conduct a survey or a measurement. It's not something you can find from a calculation. That's the idea. And we're going to talk more about random variables when we get into probability. But we have a few categories of variables that we're going to see as we go through the course. Qualitative, sometimes these are also called, you'll see it called categorical. Qualitative variables are either non-numeric, they don't involve numbers, or they're not used in any type of calculation. Quantitative variables are variables that you would form a calculation on. They're numerical measures. You can find the average, you can find the sum, you can find the spread of the data. So these are numerical. Most of what we're going to be dealing with in this course, up to the very last lesson, almost everything we do in this course is going to be with quantitative. And within quantitative, you have another distinction that needs to be made, and this will have an effect on the graphs and the type of analyses, the type of distributions we can see for a data set. A discrete variable, and these are subsets, you can tell the indents, these are subsets of quantitative. A discrete variable has a fixed set of possible values. The classic example is the six-sided die. If you roll a die and X is the result of the die roll, well, X can only have 6 values. It can be a 1, 2, 3, 4, 5, or 6. That's it. You're limited to those 6 values. A continuous random variable has either an infinite number of possible values and can be measured to any desired level of really precision, I should say, not accuracy. But there's a continuum. There is an infinite, or at least very, very large number of possible values. And we'll see this in more detail in upcoming lessons. I just want to finish up with some just examples of, just to kind of bring this home. Qualitative variables. So favorite color, political party, result of a coin flip, heads or tails. These are not numbers. You can't do any calculations on them. You can't find an average color. Well, I guess if you do RGB values, maybe, but generally you can't find an average color. They're words. They're non-numeric. Quantitative discrete. Okay, so this we talked about already. Number on a six-sided die. Number of cars in a household. So in most cases, a household is going to have 0, 1, 2, 3, maybe 4. There's only a limited number of values. I mean, we talk about Jay Leno having 1,000 cars, but most of the time you're going to have it's going to be a very fixed number. Quantitative continuous, salary of an employee in a large company. High temperature on January 1st. If you go past 100 years, on January 1st, because the temperature can be a huge range of values, especially if you go down to, say, tenths of a degree. You can't list all the possible values. You can't make a list of them. SAT scores, again, sometimes there are gray areas here, but SAT scores, they are rounded to the 10, but still, even on an individual test, it could have 800, 797, 87, 77, 60. I mean, you could, this is a slight gray area because you could list every possible SAT score. It's not infinite, but for reasons that we'll see in the next few lessons, we do have to treat this as continuous because while the number of possible values is not infinite, it is pretty large. And even if it's a very large number of possible values, in many cases, we're going to treat it as continuous. And again, the next few lessons, we'll see why that is. Okay, so this was a bit of a long lesson, but just to kind of quickly recap the most important points here. Sampling error results from not having all the data. We take a sample of data, we measure from those samples, and we try to form an inference on the population based on that sample. We talked about descriptive versus inferential. Again, that's just a 50,000-foot overview. We'll go into this in a lot more detail. And then we talked about random variables. We'll see those in more detail later. This lesson here is kind of a broad overview. We're going to see examples of discrete versus continuous, of descriptive versus inferential. We're going to see those examples in upcoming lessons. So the takeaway here is just the fact that we have samples, we have populations, and we have different types of data. If you understand that part, you're good to go for now. So thanks for watching, and I will see you in the next lesson. If there's any questions, comments, concerns, please let me know, and I'll see you in the next video. Thanks for watching.